updrafts, and if you look in the numerical simulation, you can show that they're not buoyant. And so these are dynamically forced updrafts. And we get very sharp variations in the vertical, although because the sonde is not actually falling in a vertical path, this actually contains horizontal variability as well, and many of these sharp variations are probably actually a very sharp horizontal variability as the sondes are advected into the strong updraft. And then finally, the profile here is multi-valued because the sonde is not falling in that region. So the sonde starts falling, and as it enters an updraft greater than its terminal fall speed of 10 meters per second, it starts rising. And so in this region here of the 10 to 20 meter per second updraft, it's rising before it falls again. So you get this loop in the profile. So the hypothesis is that is that extreme updrafts and near-surface wind speeds are associated with small-scale coherent vortices with a scale of less than a kilometer. Because the extreme updrafts appear to be associated with similar extremes in the horizontal wind speeds, there's a close association in this case. The region with a really strong updraft is the same as the region where you have a really strong gradient in the horizontal wind speed. So you get 102 meters per second here, but it also varies between 70 and 102 meters per second over a very small distance, either vertically or horizontally. And so this indicates there must be really strong vorticity here. So that's an example profile, but what I did is I tried to study this more systematically by creating a data set of the most extreme updrafts and wind speeds sampled by dropsondes and tropical cyclones. And this is described in this 2016 paper in Monthly Weather Review. So the data set is from 1997 to 2013, and in that time period, about 12,000 dropsondes have been dropped into tropical cyclones from NOAA and U.S. Air Force flights. And so I looked at all 12,000 of these sondes, not all individually, but I started by doing some automated quality control and searching for the strongest updrafts and wind speeds. And then dropsonde profiles that were strong enough, then I looked at closely individually and did manual quality control, because there are some errors that if you don't look at it closely, you'll miss. And so then I after careful manual quality control on all the candidate dropsondes, I finally ended up with a final data set of 169 dropsondes in 35 different tropical cyclones that had sampled an updraft stronger than 10 meters per second. And again, all of these are low-level updrafts because the flights are almost all below 3 kilometers height. And then I chose the threshold of wind speed of greater than 90 meters per second, and there are 64 sondes in 12 tropical cyclones with those wind speeds. And that's through 2013. There's been more in the last few years because there's been several very intense tropical cyclones. So this is an example of extreme updrafts and Hurricane Iris on the left and Hurricane Francis on the right. These are vertical profiles of vertical velocity. The flight level is shown with a black dashed line. 0 meters per second is this red vertical line. The scale of these plots isn't exactly the same, but it goes from about negative 14 to positive 24 meters per second. So these both show examples of updrafts of about 17 meters per second at only 600 meters height. So within the boundary layer, very close to the surface, and you get very strong rapid fluctuations between, sometimes you get very strong downdrafts. This is a 12 meter per second downdraft, very nearby the 20 meter per second updraft. And I've highlighted on here the maximum vertical velocity, which you can see from the line. I just indicate with the red dot, but the green dot indicates the height at which the maximum wind speed was found for this sonde. So in some of the dropsonde profiles, you find a close correspondence between the height of the maximum wind speed and the height of the maximum updraft. So this Hurricane Francis sonde is a good example of that. It's right in the same region, You have the peak updraft and the peak wind speed located close to each other. So that's evidence that these extremes might be related to each other. And this is an example of two other sondes to show some of the more extreme wind speeds that we see. And so Hurricane Rita on the left and Hurricane Dean on the right, and these are both Category 5 storms. And here we have 90 meter per second wind speeds or greater at less than 100 meters height. So this, you could imagine, could cause a lot of damage if it were to make landfall with a structure like this. Again, in this case, there's the maximum vertical velocity is located closely to where the maximum wind speed is. This is the strongest wind speed ever sampled by a dropsonde in Super Typhoon Meggy in 2010 in the Western Pacific. There was a field campaign, and so there were dropsonde with flights into the Meggy. And Meggy has most of the strongest dropsonde sampled winds that we've seen. I believe it had 6 dropsondes sampling greater than 100 meters per second. So in this case, you have a very deep profile of 80 to 90 meter per second winds, and then this jet at about 150 meters height, that's 111 meters per second.
Excuse me.
Yes?
Probably this is a very basic question. How is the frequency of sampling frequency from there for vertical resolution is data?
Mm-hmm. So the wind speed in the more recent sondes are sampled at 4 hertz, so 4 times per second. The older sondes were twice a second, and so when the sonde falls at about 10 to 12 meters per second, the older sondes would have a vertical resolution of about 5 to 6 meters, and the newer sondes are more like 2 to 3 meters vertically. That's what the raw data is. There's when you do the quality control, you typically apply some amount of filtering and smoothing with a time scale of 5 to 10 seconds. So that means that you're usually not resolving scales of 2 to 3 meters, but a little bit more than that. But the data itself is calculated over at 4 hertz for the new sondes. So currently sondes are 4 times per second for wind speed.
Different question. So typically we lost the signals below 100 meters, for example, in this case, right? Do you know the reason why?
So my understanding is that you get large accelerations horizontally and vertically near the surface, and that can make it hard for the GPS signal to track. I don't know the details of the engineering of it, but that's been a common problem with dropsondes. It's something that's been improved over time. The dropsondes today are report much more often near the surface than they did 10, 15 years ago. And in fact, there is some missing data here, but actually you can see there is dots there. So some of this is a consequence of the quality control. So these are post-process quality control data, and sometimes more data tends to get removed in regions of very large gradients.
I'm sorry, yeah, I now noticed that. So in this case, surface wind is about 70 or 75 meters per second.
Yes, in this case it is. Although sometimes so when we talk about surface wind, usually we standardize it to mean 10 meters.
10 meters.
And the dropsonde might report below 10 meters height, so you have to be careful. Sometimes the data might be from 2 meters or 3 meters, and if that's the case, the wind there is going to be less.
Right.
It's hard, with looking just visually here, it can be hard to figure out what the 10-meter wind is. And I should also say that there's uncertainty in the height of the dropsonde, so the GPS might be only accurate between 20 or 30 meters. The heights are usually actually assigned by integrating the pressure hydrostatically. And so what's generally done is you assume that the dropsonde reported all the way to the surface, and the lowest point is equals 0, and then you integrate the temperature and pressure upwards to flight level to get the height, because that's deemed more reliable than the GPS itself. But that depends on knowing that the sonde actually had data all the way to the surface. And if the sonde didn't have data, if the sonde failed at 50 meters, you might not actually be able to tell that. And so then your height can be off systematically by 50 meters.
Right. So now, what I'm thinking is a little bit, strange thing.
Yeah.
Like in this kind of very extreme case, maybe wave height is almost 10 meters.
Yeah.
Right. And also, sea spray almost cover the ocean very
Yes.
much dense way.
Yeah.
So I think it's very difficult to define, lowest
Yeah,
level.
I agree.
Where, which level we can get the lowest, level. So that's my.
I think that's true, and I think that's a lot of we don't really know. We don't know whether it hit. What happens if it hits a wave crest versus a wave trough, and where the surface becomes kind of ill-defined. And so for that reason, along with the fact that, like I said, sometimes you don't know what the height is because you don't know if it failed before it hit the surface. There's some uncertainty. It's not like hundreds of meters, but it could be 10 meters or 20 meters.
Yes.
And for most purposes, that doesn't matter. So like knowing like this is at 150 meters versus 160 meters, that doesn't really matter. But if you wanted to know accurately the surface wind or the 10-meter wind, that could make a huge difference.
Right.
Because if what you thought was 10 meters was really 50 meters, that matters. And if what you thought was 10 meters was really 2 meters, that matters for interpreting how strong the winds are and how the decay is in the surface. So I would caution. I think it's difficult to look at really near the
What
surface
is
winds with a 10-meter wind for the drop sondes.
Yes, thank you very much.
Excuse me. So, in that case, what was the vertical motion? So, what was ascending or descending at the maximum wind speed around the world?
I'm not sure. I'd have to look back at it. I don't have a plot of this one right here, and I think it was. Well, I can tell you the peak wind speed.
Yeah.
The peak vertical wind speed in this case is the red dot, so it was actually near flight level.
Yes.
And that's consistent with the shape of this profile of wind speed. So this indicates that the sonde was dropped well into the eyewall because the winds are close to constant over a deep layer, which would be consistent with it being dropped in the flight level eyewall updraft. I don't know whether there was an updraft here or not. I think there probably was an updraft, but I'm not sure how strong it was.
Mm-hmm.
This is the strongest updraft measured in a tropical cyclone by a dropsonde. This is from Hurricane Patricia in 2015. You notice that there's no data below 2,200 meters, which is actually the flight level, and that's because so the sonde was dropped here, and then it immediately started rising because it was dropped into a 10 meter per second updraft. And then the updraft became as strong as 27 meters per second, and the sonde rose by over a kilometer, and then it failed at 3,200 meters, a kilometer above where it was dropped, and then there's just no data below that. But this is an incredibly strong updraft near and above flight level, and you can also see there's a lot of variation. And this just shows the time series of the height of the sonde. So unlike most dropsondes that go down, this one just kept going up and up.
So I failed to, maybe I missed to hear about technique to measure the vertical motion. So you assume the terminal velocity of zone body, or is a direct measurement of vertical velocity?
It's measuring the vertical velocity of the sonde, and the sonde will have a vertical velocity due to its fall speed, and that's generally known.
Altitude is measured by GPS, and
The altitude is measured by the GPS, but it's also measured by integrating the hydrostatic equation.
Yes.
And so they're both used sort of in the quality control procedure as a check on each other. But generally, the final height comes from the hydrostatically integrated height if if it is believed that there's good data to the surface, you integrate upwards hydrostatically and get the heights from that.
Yes.
If you think it failed before the surface, then you end up with no heights assigned. But you could look at the GPS height to see where you think it is, because GPS is pretty accurate. The vertical velocity in the final product, the vertical velocities I'm showing you, this comes from vertically from the time tendency of the pressure from the hydrostatic pressure, or the time tendency of the heights that come from integrating the pressure.
So this includes the fall velocity of the sounding itself. So
Yes. So
you
then,
you have to sub.
yeah, you subtract, and this is all done within NCAR's software called Aspen for quality control of sondes. And you know the sonde mass, the weight, the size of the parachute, and the drag coefficient of the sonde was derived from wind tunnel measurements, and so there's an equation for the terminal fall speed of the sonde as a function of the air density, and that's relatively accurate, probably within a meter per second, and so you know approximately how fast it would fall if there were no vertical air motion, and so you just subtract that from the sonde velocity, which is what you've measured, and that gives you the analysis or the estimate of the vertical wind speed.
So the estimation error is within several meter per second.
I would say like plus minus 1 meter per second. So for anything more than like 5 or 10 meters per second, that's an acceptable error. The sondes are not going to be useful for measuring weak motion. Like you could not use them to measure subsidence in the eye, for example. It's too uncertain, too much error. But for measuring large updrafts and large downdrafts, it's generally reliable. Yes. So this is from the observational data set. This is the distribution of the updrafts on the left and on the wind speeds on the right. So again, the threshold vertical velocity for the data set is all sondes that sample W greater than 10 meters per second somewhere. And then for the wind speed data set, it's all sondes that sample greater than 90 meters per second. As might be expected, you have more sondes that are towards the weaker end of the threshold, and decreasing frequency as you get to higher and higher vertical velocities and wind speeds. But you do have sondes that are as strong as 15 to 25 meters per second. The Patricia sonde I just showed you was not actually in this data set, it was after that time. So that would be out here at about 27 meters per second. And then for wind speed, most of them are between 90 and 100 meters per second, but there are 8 sondes greater than 100 meters per second. 6 of them from Super Typhoon Megi. And the others one from Isabel and one from Ivan. And then there have been a few sondes, I believe, from Hurricane Maria last year that also had greater than 100 meters per second. And this is the relationship of the data set of the frequency of these sondes with storm intensity. So the x-axis here is the best track intensity in knots. And so first looking at the right, this is not surprising. All of the sondes sampling extreme wind gusts were dropped in very strong hurricanes. So all of them are category 4 and 5 storms. More interesting is that a large majority of the strongest updrafts are also from category 4 and 5 storms, and 90% of them are from major hurricanes, category 3 through 5. There occasionally are strong updrafts sampled at low levels in weaker storms, but it's much more rare compared to the strong storms. So there's an indication that the updraft strength at low levels is probably related to the intensity of the storm. Some people have suggested or speculated that there might be a relationship with the intensity tendency, whether a storm might be rapidly developing or steady state. And actually, well, I'll skip to that for a second. So it turns out, from the data set at least, there is not any clear relationship. This is the 6-hour intensity change in knots for the updraft signs on the left and the wind speed signs on the right, and there isn't a clear relationship. There's slightly more strengthening storms with updrafts than weakening storms, but that's probably because on average there are more storms that are found to be strengthening at any given time than that are weakening. So if you look at the data set of all SONs, there are more cases that are strengthening. So this is very similar to just the distribution of all dropsondes. So if there is a relationship between intensity change and these extreme updrafts, it isn't something that it isn't a clear tendency. It isn't a strong relationship because it doesn't come out in this data set. Just going back quickly here, this is a scatter plot of the best track intensity versus the maximum vertical velocity. So before I was showing you just the frequency distribution. This is the maximum vertical velocity versus the intensity, and on the right the maximum wind speed versus the intensity, so the mean intensity of the storm. And interestingly, there's not really any correlation of the wind speed and updraft magnitudes with GC intensity. And I think we should expect that there is a relationship, especially for wind speed. The strongest wind gusts should probably be in the storms that have the strongest mean intensity. And so I think this is probably related to just limited sampling from observations. There's only 64 SONs here in the right plot. And so I think if we were able to have a more robust, larger data set, we would find that there's a relationship between the gust strength and the mean wind speed. And there probably is a relationship between the updraft strength and the mean intensity as well. But it's just something we don't have enough data to find that, is my guess. This shows, there's a lot going on in these plots. This shows the radius, height, location of where these SONs are found. Just focus mainly on the red dots. That's the location where the maximum itself is found. And so on the left is the updraft SONs, and you can see we find them over a fairly wide radial range. But this is because they were sampling storms of different size. And it turns out these are almost all in the eyewall of the storm. So sometimes we have large storms like Hurricane Isabel, and sometimes we have small storms like Hurricane Patricia. But all of these are in the eyewall region. And their height, they can be found anywhere below flight level. So the updrafts are found over a fairly broad region, sometimes as low as a couple hundred meters above the surface, sometimes near flight level. On the other hand, you can see there's a difference for the wind speed, the extreme wind speed SONs on the right. They're confined to a much lower layer. All of them are below 1,400 meters height. So the most extreme wind speeds are generally found in a shallower layer than the most extreme updrafts. And we can see this another way by looking at the distributions of the height of the maximum vertical velocity on the left and the height of the maximum wind speed on the right. And for the x-axes here are different. The scale goes from 0 to 5,000 meters for the updraft plot and 0 to 1,500 meters for the wind speed plot. So you can see that the wind speeds in the observations, there's a pronounced peak at about 400 to 600 meters height, which is actually, that's very similar to where studies have suggested that the mean wind speed is strongest. But we do still have some SONs that they found the peak wind speeds were less than 200 or even less than 100 meters above the surface. For the updrafts, like that previous plot, there's a much wider distribution, and many SONs are found at 3 kilometers, at 2 kilometers, or less than 500 meters. So the extreme updrafts occur over a deeper layer than the extreme wind speeds. And this shows the magnitude of the updrafts on the left and of the wind speeds on the right as a function of the height at which those peaks were found. And you can see the wide range of heights that the updrafts are found over. And also, there isn't an obvious relationship between the magnitude of the peak updraft and the height at which it's found. And similarly, there isn't a clear relationship for the peak wind speed magnitude and the height at which it's found. And it's possible that limited in sampling is also contributing to this. And in the end, we're fundamentally limited by our ability to drop large numbers of dropsondes in the Eyewall region of tropical cyclones. Because a single dropsonde is just going to sample just one trajectory, and the sampling is sparse, and it's hard to sample the maximum wind or the maximum updraft. And we can't see the three-dimensional structure of these features from dropsondes. And like I showed you earlier, it's just not safe to fly an aircraft in the boundary layer in the eyewall, so we can't directly sample with the aircraft either. So I think we can gain further insight by going to simulations, and I'm going to show some results from large eddy simulations here. So I'll briefly just go over like what we've seen from some cloud permitting simulations, so some non-LES simulations. This is a study from Gentry and Lackman, looking at the vertical velocity of a simulated Hurricane Ivan as they systematically increased the resolution, decreased the horizontal grid spacing from 8 to 1 kilometer. And they found that as you decrease the grid spacing, increase the resolution, you get more detailed structures and hopefully more realistic structures. Although sometimes it's hard to tell if it's more realistic or not because we don't have as good observations. They also found that as you get to finer grid spacings, the updrafts tend to get stronger. It's not possible to see the scale here, but you can see the colors get more darker reds here, so you're getting stronger and stronger updrafts. You're getting smaller updrafts, and the inner core itself tends to get smaller as you're better resolving the eyewall. Another study is from Fierro et al., and they looked at a simulation of Hurricane Rita as they systematically decreased the grid spacing from 5 at the bottom to 1 kilometer at the top here. On the left is simulated radar reflectivity, middle is vertical velocity, and the right is wind speed. And they found that as grid spacing decreases, again, you get more detailed, possibly more realistic structures, stronger updrafts, the inner core gets smaller. They also found that the eyewall decreases in width. You get a narrower eyewall for the smaller storms and finer resolution. The area of strong winds they also found decreases. So, as you go, yes.
Excuse me, can I ask a question on the Dropsonde observation? Could you please back to the Sonde observation? The last slide of. I'm wondering this one. The maximum vertical velocity seems to appear outside the inflow boundary layer, tropical cyclone inflow boundary layer. I'm just wondering the location, radial location of the maximum vertical velocity and maximum wind speed appear. It is in the inflow boundary layer, or just edge of boundary layer, or interface of boundary layer.
Well, so all these suns above about a kilometer are above the inflow layer. These are going to be an outflow. I don't have the plot here, but in the paper I show that they're all almost all between within 10 kilometers of inside of the RMW at flight level and at the RMW. So they're all dropped within the eyewall. And so the lower suns here are probably within the inflow boundary layer. So some of the updrafts are in the inflow layer, some of them are in the outflow layer.
So how about the maximum wind speed?
The low level ones are certainly within the inflow layer. And the upper ones might be as well because the inflow layer is going to change with the radius of the storm. I'd have to check more carefully to see whether they're with inflow or outflow.